Hi y'all. In this video we're going to be looking at what happens when we add water across an alkene. We have three mechanisms for this. The simplest to carry out is what's called acid-catalyzed hydration, and that's where we'll start. So all of these are hydration mechanisms. They're all going to be adding water. This one, like it sounds, we need a source of water and we need a source of protons, an acid. Importantly, we want that acid to have a large counter ion, like sulfate or phosphate. So sulfuric acid or phosphoric acid are great. If we use something small that has a better nucleophile as its counter ion, like hydrochloric acid, we can do a slightly different process where we'll be adding HX in the presence of water, and we'll talk about that one in another video. As for right now, we'll use the example of treating our simple alkene, 1-butene, with something like sulfuric acid. So this could be listed as either H plus in water, or it could be listed as sulfuric acid or phosphoric acid. It's important for us to remember, though, that water wouldn't actually exist as H2O in the presence of an acid. And so we're going to indicate this as H3O, the hydronium ion. And for the purposes of what we're drawing here, I want to separate out at least one of the hydrogens so that we can see what's going on. Step one of this mechanism is exactly the same as what we've seen before, that the nucleophilic pi bond attacks one of the positive parts of this binary reagent to give us an intermediate that follows Markovnikov's rule, so we get the hydrogen added to the end. We get the more stable carbocation intermediate. And so if we had rearrangement as a possibility, we could have a hydride shift or a methyl shift at this point. For this particular molecule, we don't have that as an option. The other piece that we had left over is, of course, water, which is left over from the original attack. That would have been the negatively polarized part of what we were dealing with. That water now, just like in the previous mechanisms, nucleophilic oxygen can attack the carbocation intermediate. This would all be classified as our transition state. The initial product that we would have to draw then would show water here, like that. Or if we wanted to be a little bit more explicit, we could say water looking like that. So our positively charged oxygen we know is not the most stable incarnation of this molecule, that oxygen would prefer to be neutral if we want to give it some feelings. And so what we have is this deprotonation event that would occur. I'm drawing water as our base because it's the most likely base that's around. It's in the greatest quantity. We could have had, for instance, the bicarbonate ion, bisulfate ion, except that that would then regenerate a strong acid. So our most common thing is water molecule. In many organic texts, you'll just see this drawn as some generic base. We don't particularly care what it is. That's just serving the purpose of taking off that extra proton so we get a neutral water molecule, neutral oxygen. And so our product then is an alcohol. And this follows Markovnikov's rule, and it goes through a C+ intermediate, which we always have to consider rearrangement as a possibility. We'll look at the other two mechanisms for hydration going forward in different videos, one of which is called oxymercuration and demercuration. It's one mechanism to do this exact same reaction, but not going through a carbocation intermediate. The other one that we'll talk about is called hydroboration oxidation. That allows us to do the same kind of a reaction, but with a reversed regioselectivity. So following the opposite of Markovnikov's rule, or what we sometimes call a non-Markovnikov or anti-Markovnikov addition. So we'll see those in other videos.